Hey guys, it's Mr. Sheeline here for the Check Your Understandings, understanding questions for Unit 4.2, the power, from the power notes. Okay, so just like last time, I'm not going to be writing down the questions, so make sure you've got the questions with you in front of you while we go through these. Okay, so we're just going to get straight to it. So check your understanding number one. So check your understanding number one. Okay. So a 51 kilogram student climbs a 3 meter tall, or 3 meters up a ladder in 4.7 seconds. Calculate the student's gravitational potential energy at the top of the climb. Okay, and then also for the power for the climb. Okay, so now here, in this case, there's a number of things that we can do here. So here it's just asking straight out though, what's the gravitational potential energy here? So for A, what's PE? Okay, what is PE equal? Well, we're given mass, and it's 51 kilograms. We're also given distance. In this case, it's going to be height. We're given height here, which is 3 meters. And we are also given time here. So we are also given time, which is 4.7 seconds. So we're just going to calculate the potential energy. And remember, potential energy, I know we just learned this, but potential energy is going to be mass times the acceleration due to gravity times height. So I'm going to write G over here. And remember, G is 9.8 meters per second squared. So all we got to do really is just plug this in. Plug in for mass, plug in for G, plug in for H. So here it's going to be 51 times G, which is 9.8, times the height, which is 3. And the potential energy that this individual has at this height, getting my calculator out, my handy dandy calculator, it's going to be 51 times 9.8 times 3, which is going to give me here an answer of roughly 1,499.4 joules. Or remember, it's 1,499.4 Newton meters, or it's 1,499.4 kilograms by meters squared over seconds squared. So whichever one works out is fine. If you were to put this in scientific notation, it would be, and also to keep sig figs, it would be 1.5 times 10 to the third power joules. Okay, so any of these would work here as the answer is concerned. So here we found the gravitational potential energy. Okay, so now we've got to find out what P is equal to. What is the amount of power that was put into this to go from, say, 0 up to 3 meters? Well, we've got the amount of energy. Okay, so we can just still put PE, or we'll put E is equal to 1,499.4 joules. We have time, 4.7 seconds, because we need those two, because remember, power is going to be equal to work times time. Now, this up here, remember, is our work. So we really could put W's all for this, okay? So this is the amount of work done up here, okay? So that's right. So I should have put it right here. So the amount of work that was put into the system was 1,499.4 joules. Okay. Now they were able to produce that in 4.7 seconds. So what was the power? Well, again, power is going to be your work times time. Or sorry, not, oh my goodness, not times time, divided by time. Yikes. Divided by time. My bad. If I confused you right there, I'm so sorry. It's divided by time because it's a rate. It's how much energy was used up over time. So it's going to be, power is equal to, again, work over time, which in this case is going to be 1,499.4 joules worth of work over 4.7 seconds, which when we plot that into our calculator, 1,499.4 divided by 4.7 should give us here roughly 319 joules per second, or 319 watts. Okay, now I know, and here I'll write it like this, watts. I know that these W's are going to get confusing, but just make sure that you understand the difference between the abbreviation for work and the abbreviation for watts, because it is also just W, and it's a capital W as well, which kind of sucks. Which there are other denotions of work, I just don't really use them, and hopefully it won't be too confusing for you. If it is, talk to me and maybe we can work something out where you use something else, and I know that you're going to use that. So anyway, so that is check your understanding number 1. So again, for B, we have 319 watts of energy. And then, or just watts used. And then here, our answers up here, again, because all of these could be our potential answers. The amount of work that was put into the system was 1,499.4 joules. Okay. So let's now move on to number 2. So check your understanding number 2. Okay. So an 85 kilogram man climbs from a height of 2,900 meters to 3,640 meters in 60 minutes. What is the man's average power? Okay, so here's what's given to us. We're given mass, which mass is 85 kilograms, and we're given 2 different heights. So here we just have to find out how high this guy climbed from one height to another. So the idea is that it's to think that the 2,900 meters is 0, and then whatever his new height is, that is going to be the amount he climbed here. So height is just going to be equal to the 3,640 minus the 2,900, which is going to be, so 3,640 minus 290. So realistically speaking, this dude just climbed 740 meters. Okay. So we don't want to use either one of these. We're wanting to use this because we're starting here and we're ending here. Okay, we're climbing up. So in this case, because we're climbing up here, we climbed up 740 meters specifically. Okay, so we've got our height, we've got time, and this guy did it in 60 minutes, which is 1 hour, but we need to change it to seconds because remember, power is in seconds, so we got to change that. So that's going to be 3,600 seconds. How do I know that? Remember, it's just, or wait a minute, no, or yeah, sorry, yeah, it would be 60 because there are 60 seconds in a minute. It would be 60 times 60, and 60 times 60 is 3,600 seconds. And that's all they give us, but remember we also do have G as well. So G is going to be 9.8 meters per second squared, and we're trying to find power. So before we can find power, we need to find work. And remember, in this case, work is going to be equal to potential energy, and we don't have that yet. So we need to figure out what the potential energy is. Okay. So here we're just going to do, work or potential energy is equal to mgh. So that'll be the mass, so 85 times gravity, 9.8 times height, which is 740. We'll squeeze it all in there. So 85 times 9.8 times 740, which it looks like, because it's a pretty good amount of a pretty good height here, this dude used up 616,420 joules worth of energy in order to go from here to here. Okay, so we'll say that this is the work done. So remember, P is then equal to W over T. Okay, so it's going to be then the 616,420 divided by 3,600. Oops, sorry about that. So then our power here is going to be 171.2 watts, okay, or 171.2 joules per second. Okay, both of these would work out for the amount of energy used here. So again, in order for this dude to climb this mountain here, so for him to go from here to here, so from here to here, he used up this amount of energy, took them this amount of time right here, and with this energy and with this time, we're able to figure out how much he spent per second. In this case, he spent 171 joules every second, or to say that he used up 171.2 watts. Okay. All right. So let's check your understanding number 2. Let's check out number 3. So check your understanding number 3. So the power rating of the world's largest wind generator is 3.0 megawatts. How long would it take such a generator to produce 1 times 10 to the 12th power joules, the amount of energy needed to launch a rocket, in days? Okay, so this one's, I love this one because it just takes a lot of like converting. That's really all it is. Also 12. I looked this up. I can't remember. I used to remember all the prefixes, but I can't remember what comes after giga, because this would be the amount of joules after giga. And I want to, it's tera, duh. So it's saying here, how long would it take a generator to produce 1 terawatt of energy, or sorry, 1 terajoule of energy, 1 terajoule of energy, and they want to know how much energy over a span of days. So okay, so anyway, so let's take a look here. So we're given, so the world's largest generator is or the power rating. So we have power equaling 3.0 megawatts, which if we were to take that down, that would be, again, because this is 1 times 10. Not to the 3rd power, but to the 6th power. So it would just be like 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So it would be 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. So that's just 3 million watts. Okay? Which is also, remember, 3 million, it'll be 3 million joules per second. Okay, so we've got power, and they also and they ask us how long, so they're asking for time, how long would it take such a generator to produce this amount of energy, or this amount of work, okay, work or energy, whatever we want to specifically call it, which is 1 times 10 to the 12th joules, which again is also, that's 1, I think that's, what is that, is that trillion? So million, billion, yeah, so this is 1 trillion. Okay, there's million, billion, trillion. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I think I've got, hold up. Million, billion, that's right. Oops, I put 1 too many groupings of zeros, because this is 1 trillion. Here's where it starts at 1 trillion. So 1 trillion joules. Okay, how much time is needed? So this is pretty easy, if you know. And again, it just takes some converting here. So P is going to be equal to W over T. We're trying to find T here, so we're going to shove T over here. We're going to do that right here. So T will be equal to work over power. Okay, and the work that we are talking about here, the work is 1 trillion joules. 1, 2, 3, 4, 1, 2, 3, 1. So 1 trillion joules over 3 million joules per second. Okay, so we're wanting to know, in this case, as you can see here, the way the units are going to work themselves out is that we can see here the joules will cancel each other out, and because you have a dividing unit in the denominator, in a denominator, or as a denominator within a denominator, that must mean then that the seconds then boost back up to the numerator, which then means that we're left with just seconds here. So just easy peasy. So 1 trillion divided by 3 million. Which is then going to give us 3.3, pretty almost 3.3 repeating, sorry, 0.3 repeating seconds. So in this case, it's going to be 333,333.3 seconds that it takes in order to produce this amount of work when it pumps out this amount of power per second. So let's just then do this. So now we got to convert this from seconds to days. So easy peasy. Just some dimensional analysis here. So seconds. So we want to first convert this to minutes. So in 1 minute, you have 60 seconds. And then minutes to hours. So actually, we'll skip this. What we're going to do straight to hours. So it's 3,000. 1 hour is 3,600 seconds. So we've got hours here, and now it's just straight from hours to days. So there are 24 hours in 1 day. And then we will get our number here. So 333.3 all times 1 divided by, and then it'll be 3,600 times 24. Oop. And we'll see here that it takes 333,333.3 seconds, or 3.85 days in order to produce this amount of energy, that amount of work at this rate. Okay, easy peasy. So 3.85 or 3.9 days for our answer there. Okay, so check your understanding number 4. So the nuclear generator station located in Pickering, Ontario, is rated at 2,160 megawatts of electrical power outlet. How much electrical energy in megajoules can this station produce in 1 day? So here's just another simple conversion conversion problem. So they give us here, for check your understanding number 4, they give us here, power, and power here is 2,160 megawatts. They also give us time. Time is 1 day, and they want to know the amount of work done here, how much energy, okay, can be produced here. So 2160 megawatts. So let's just quick convert that into just watts. So again, remember, this is 1 megawatt is equal to 1 times 10 to the 6th power. This would just be, and then 1, 2, 3, 4, 5, 6. That should work out. 1, 2, 3, 4, 5, 6. Yep. So that's going to be 2,160,000,000 joule or watts. And then 1 day, we just got to convert 1 day into seconds. So there are 24 hours in 1 day, and then the 24 hours times 3,600 seconds is going to be 86,400 seconds. So, and I can show you I'll show you all the way at the bottom here. So this is how I did that. So 1 day times, and then just 1 day again, and then 24 hours. And I know that there are, in 1 hour, there's 3,600 seconds. So those cancel out, that cancels out. So then 1 times 24 times 3,600. So, and that gives me the 86400 seconds. Okay, so we've got wattage, we've got seconds, so now we can find how much energy. So let's just do that, because we know that P is going to be equal to W over T. Okay, so let's just put that again over here and plug everything. Oh, and we got to solve for W. So it'll just be P times T. So W is equal to P times T. And that's going to be, oh boy, 2,160,000,000 watts times 86 8,400 seconds. 123 times 8,600, which is then going to give us 1.87 times 10 to the 14th, 1 times 10 to the 14th joules. And it doesn't say here, how much energy in megajoules. So if it needs to be in megajoules here, then it's just going to be 14 minus 6. So then it'd be 1.87 times 10 to the 8th power megajoules, MJ. And I'll go through real quick on just to remind you how that works out in scientific notation. So if we've got 1.87 times 10 to the 14th, and if megajoules are equal to 1 times 10 to the 6th power, it's just subtracting the exponents here. So it's literally just 14 minus 6, which is 8. Another way you could show this is to say this. You'd have 1, 8, 7, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And you fill all those zeros in. So 1, 8, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this right here is the same thing as this guy right here, but we want to have them in megajoules. So, and if megajoules are 1 to the 6th power, it'd be like taking your decimal from right here and just moving it 6 places to the left. So it'd be like 1, 2, 3, 4, 5, 6, putting it there. So then you would have 8, 1, 8, 7, 1, 2, 3, 1, 2, 3, which then if you counted, if your decimal's right here, it'd be 1, 2, 3, 4, 5, 6, 7, 8, which would then be 1.87 times 10 to the 8th power, in this case, megajoules. Okay, which is a lot of energy. That would be, in gigajoules, that would be 1.87 times 10 to the 5th power gigajoules, and then that would be 1.87 times 10 to the 2nd power for terajoules. Okay, so just a quick little reminder on scientific notation, and since we haven't done that in a hot minute, okay, or you probably haven't done that in a hot minute, okay, and then check your understanding number 5 here. So let's check your understanding. So CU number 5. Okay, so Lamborghini, however you pronounce that particular model, or let's see, Lamborghini is Italian, I think. So Lamborghini, Murcielago, duh. I guess I never really see it written. I completely forgot how to pronounce it. Yeah, the Murcielago is the LP670 for super. Now this one I really actually don't know how to pronounce, but Veloce, I would imagine, super veloce, super velocity, I'm sure in Italian is what that means, has a weight of 3,450 pounds and can go from 0 to 60 miles per hour in 2.8 seconds. What is the average power output of the car's engine in kilowatts? Okay, so let's just try the best that we can here. So, and we kind of already know this answer again from the notes because that was kind of given away to us. But let's see, so the weight. So the weight here, and the weight is going to be, in this case, technically speaking, it would be F sub G, so the force, because remember weight is a force. But it just so happens instead of being in newtons, it's just in pounds. So we're going to have to convert pounds to newtons here. We'll have to convert this from pounds to newtons here. And then on top of that, we also are given acceleration, and we're given pretty much just, they were given acceleration here, which is initial velocity in this case, it's going to be in miles per hour is 0, and final is going to be in 60 miles per hour. And we're also given time here, which time is, thank God, in seconds. What is the average power output of the car's engine in kilowatts? So what we're trying to find here is how much energy is this, on average, how much energy is this expelling, okay? And on top of that, how much energy per second. Okay, so we've got some converting to do. We've got some converting to do here, so let's just kind of walk through this. I honestly kind of forgot that we had to do this much converting in this question, to be honest with you. So I'm a little caught off guard here, so let's just kind of let's do this in real time. Screw it, we're doing it live. Oh, Bill O'Reilly. So let's convert our pounds to, let's just convert our pounds to newtons, because it seems, I'm saying that just because it seems like the right thing to do here. So pounds to newtons, just a quick Google, because I don't even have that at the top of my head. So we've got 3,450. So that's going to be roughly equal to 15,346.4 newtons. We got to change this to meters per second, which thank God, that's so easy. Here I'm going to use this guy to quick do the 60. So 60 miles per hour. We got to change miles to meters and then hours to seconds. So that's going to be, we're going to get miles first. So in, let's see. Oh boy. Oh my goodness, I'm blanking. In 1 mile, let's see, in 1 mile there are, no, I know this the other way around. In 1 kilometer, there's 0.621. There are 0.621 miles in 1 kilometer, okay? And then, so we've got miles there, now we're in kilometers, but now we need to go from kilometers to meters. Okay, and there's 1,000 meters in a kilometer. Okay, now we're in meters, and then from hours to seconds is pretty easy. 1 hour, there are 3,600 seconds. So putting that all together, so 60 times 1,000, then divided by 0.621 times 3,600. So this person is going 26.8 meters per second. Okay. Cool beans. All right. Now again, because this one's a little tricky. A lot of converting, and there's some things that are given, some things that are not given. Okay, so what do we know? Well, we know that, oh, and the pounds should also be converted more to mass than anything. So real quick, let's just do that. So 15,346 divided by 9.8. So mass is going to be 1,566 kilograms. Okay, so we got mass as well. Okay, so let's see here. So we've got mass, we've got force due to gravity, we have initial velocity, we have final velocity, we have time. So let's just find acceleration. We may not need acceleration, but we're gonna see. But we may need acceleration here. Okay, so let's see here. Let's see, acceleration in this case is going to be 26.8 minus 0 over 2.8. So acceleration is going to be 9.57 meters per second squared. Okay, so now we've got acceleration, which is pretty cool. It's our remember, this is our average acceleration. Okay, so we're already working with averages here. Okay, so average acceleration, so we really don't need to worry about this really much anymore. We've got time, we've got acceleration, we've got mass. So then what you should be thinking is that, okay, in order to figure out work, because we need work in order to find power, well, work is going to be equal to force times distance. Okay, well, we don't have work. Oops. We don't have work, and we don't have force, but we could figure out what the force is real quick here. And then we can also figure out what the distance traveled here is. So whatever answer I put in the notes, like in the speaker key, may be a little different. But let's just see here. We may be off by a decent chunk just because we're deriving, and if I remember correctly, there's more of just substituting in this question than anything. We're actually solving for each of these bad boys here. So let's just see what happens. So, okay. We need to find force because force times distance is equal to work, and when we have work, then we can find our power. We can find out how many watts were expelled here. So let's try to find force. So force is going to be, of course, force is equal to ma, and we're completely negating friction here. We're just focusing on this. So mass times acceleration. Okay, so we're going to use that bad boy up here. So F is going to be equal to mass, which is 1,566, times our acceleration, which is 9.57. 1566 times 9.57, which is going to give us a force of 14,986.2 newtons. Okay, so we've got force now. Cool. Awesome. We're on a roll. So we've got force. Now we just have to find out distance. Now, this is where those kinematic equations can come in to figure out how far it is that this individual went in this time, this amount of time. Okay. You could use the average acceleration, or we could use the average acceleration with a kinematic equation in order to find d, which would be the vf squared is equal to vi squared plus 2ad. Now we can find it like this, or we could just, or you could find it using the velocity, average velocity equation. Either one doesn't really matter. You should get the same result either way. Oh, this is also squared. Let's just use this because I've got this here. So we're trying to find distance here, displacement. So we're just going to solve for displacement. This guy we don't even need because it's 0. So it's going to be vf squared divided by 2 times acceleration is equal to d. And then d, to plug everything in here, d is going to be final velocity, which is 26.8 squared over 2 times the 9.57. So then when it starts at rest and then reaches its final velocity of 26.8 meters per second or 60 miles per hour, it has gone 26.8 squared divided by 2 times 9.57. It has traveled 37.5 meters. Okay, which that's roughly speaking, that's about, let's see, I think I just did the wrong, that's the wrong thing. Let's see, divided by 3. 37, that's 37 meters. Why can't, that'd be, divided by 3, so feet. So that's, or no, times 3. So that's roughly about 112 feet, which is 113 feet, or give or take, that's not very far. So that's pretty cool. So now we have distance. So let's just kind of rewrite that over here. So now we have displacement. Displacement is 37.5 meters. We have force, which is 14,986.6 newtons. Now we need to find the work done. And how much work has been done here? Well, W is equal to, work is equal to force times displacement. So that's going to be 14,986.6. Oops, ran out of space here. So times 37.5. So we then have, oops, that's not W. So we then have 14,986.6 times 37.5. We've expelled 561,997.5 joules worth of energy. And now we've got to convert that to wattage. So remember, the amount of time this happens in is in 2.8 seconds. Okay, and we know that P is equal to W over T. Okay, so then we're going to use this guy. Just plug everything in. So 561,997.5 divided by 2.8. And our power then is going to be, it's going to come out as this. Yeah, it's decently off then from what I got, or what I have in the key. So what I calculate here is 280,998, 999. We're going to try that again. 208,999 watts. Now, my key though says 201,045.47 watts. So there's quite a discrepancy here between what I just solved for and what they show, what the key that I have originally in these set of notes show here. So I might play around with this today, and I'll maybe post a quick video showing where maybe I went wrong. But as of right now, this is what we should have come up with. But it's possible I skipped something, or this is such a large discrepancy because we had to go through three or four different equations and to solve for 3 or 4 different items before we just got to this. So it's possible that just because we solve 4 different pieces first instead of just substituting, that we have this large discrepancy. So I'm going to try that out and figure out where it is that maybe it can be either closer to this, or if I get the same thing that I got here. So anyway, that's going to be it for the video, guys. If you still have any questions for me, make sure you ask. Get a hold of me in any way you can. That's the end of the video, so I'll see you guys in the next one.